Okay. Great. So this is, so last week we covered chapters 14 and 15. And then this week we're going to get into chapters 18 and maybe touch on 19 if we can just start it or get you some exposure to that. And this means we are skipping chapters 16 and 17. And that's it's a bit of a bummer for me because I do like chapters 16 and 17, but I don't think we just don't have enough time to really cover those to the I don't know, the amount that you need to cover them to give them justice. So we're just going to skip those two chapters entirely. Okay. And last week I didn't get into probability trees in chapter 15. It's like the last section in chapter 15. We didn't really get to cover that, so that's I'll start off there. And then there's a few things from maybe chapter 14, especially some wording things, especially with like the blood type problem. In particular, 32b part 3. So this is chapter 14, number 32, part B, part 3. Okay. And the preface to this says that 45% are type O, 40% are type A, what is it, 11% type B, and the rest AB, okay? Okay. So there's a distinction. So one asks, so problem 3 asks, they are not all type A, okay? Okay. And I want to point out the difference between not all type A versus all not type A, okay? Okay. Not all type A versus all are not type A. Okay, they sound similar, but they are very, very different. Okay, so not all type A, this is basically asking what is the probability that everyone is type A. Okay, and then we just do 1 minus the probability that everyone is type A. So what is the probability of all type A, but not that happening? So it's what is the probability of not everyone is type A? Okay, so that is how we would solve that one. And then all not type A means everyone is not type A. Okay, so everyone is something other than type A. Okay, and I know the homeworks are there, but you can just grab them after during break and stuff like that. Okay, so to solve this one, not all type A, we would have to find the probability that everyone is type A. So if the probability of type A is 0.4, okay, 0.4 is the probability that one person is type A, and we have 4 people. So the probability that all 4 people are type A is going to be 0.4 to the 4th, and then not that is going to be 1 minus 0.4 to the 4th, which gives us, I don't know, some pretty big, something close to 1. It's going to be like 0.9 something something. I'm not doing the math right now, okay? And then all are not type A. This would be the probability of one person not being type A, one person is going to be 1 minus 0.4, or equal to 0.6. And then what is the probability that everyone, all 4 people, are not type A is going to be 0.6 to the 4th. So over here we have 0.6 raised to the 4th, okay? So it's a subtle distinction in the wording here, but we'll have very clearly different answers. Okay. So I think this one comes out to be about 0.13-ish. Okay. Questions on this stuff?
Another one from that Chen.
Okay.
The one that says it's A number 2 that says has type A or type B. And so I understand the reasoning behind it being disjoint, but I also thought it might not necessarily be because of the type AB. Some people have both AB, so
okay, so
I wasn't clear.
type AB is so the question is on part A, part 2. What is the probability that someone has type A or type B? You're just going to take the 40% and the 11% and add those together and get 0.51 or 51%. Okay, type AB is something completely disjoint. We might as well call it type C. Okay, so it could just be type A, type B, and type C. Okay, type AB, just the funny thing about how the blood types work is that, type AB can accept blood from types A and type B, but it's really an entirely different kind of blood.
Another category.
It's another category. Okay.
Question?
Yes.
Could you give some more examples of disjoint versus independent events?
Yeah.
Okay, disjoint versus independent events. Okay, so the hardest thing is thinking about something that's disjoint. Okay, so let's say, okay, so we're going to pick a random student, and we can say the person is going to be a man or woman, okay? And we could say that the probability that a randomly selected student, okay, let's say the campus is, we're at like an engineering school, which happens just statistically, there's generally more men at engineering school. So let's say probability of selecting a man at this engineering school is 70%, and the probability of selecting a woman is 30%, okay? Meanwhile, let's say at the engineering school, we're looking at different races, and so let's say so we'll just say probability that a student is Caucasian will be let's say 55%, and then the probability that it's I guess a minority race, we'll say is 45%. Okay, so anyway, these are all disjoint, okay? Or, okay, the probability of being a man or a woman, the event that someone is a man or the event that someone is a woman, these are disjoint, okay? If somebody is a man, that person cannot at the same time be a woman, okay?
I don't know about that.
Okay, well, with the exception of the about, maybe about, I guess about, what, I don't know what the numbers are now, but about 7 in about 10,000. So there's a small population, but there are people born with traits of both male and female. It's true, but we're simplifying our world so that if you are a man, you cannot also at the same time be woman, or if you're a woman, you cannot at the same time be man. Okay. And also, if you are Caucasian, you also cannot at the same time, with the way we've categorized the people, you cannot at the same time be minority race, and if you're a minority, you cannot also at the same time be Caucasian. So these could be, these are disjoint. These two events are disjoint. And these are also disjoint, okay?
So that's excluding the idea that people can have mixed races, Caucasian and minority.
Well, just the way we categorize this, okay? And I mean, we could further break this out. So it could be Caucasian, and like in the census, they now have what is it? White, non-Hispanic, or Hispanic, and then Black, and then Asian, and just categorizing people into races is a very tricky thing. And so, every time they take the census, it's got a different number of categories of people. And a lot of it gets clouded in politics too. And so, anyway, we can categorize this, and if we were just to follow the census, we could have, some category, and all of these, according to the way the census does it, okay, these would all be separate, and all of them would be disjoint, okay? You cannot be in one category and another category at the same time, okay? And yes, now they have, I think, a box for mixed race, which is a lot more common with this most current census than census taken 40 years ago. So anyway, all of those things, if you're going to just be, those are disjoint, okay? These two, so within one thing, these are disjoint. You can't be this and this at the same time. However, the event of being male or a man and either Caucasian or Asian or whatever could be independent. It might not be independent, okay? And the only way we can find out if something is independent, okay, so independent means the two events, knowing one thing about one event gives no additional information about the other event. Okay. So, for example, let's say we're looking again at this engineering school, and 70% is male and 30% is female. Okay, so this side represents men and women. Okay, and all right, let's just for simplicity's sake, let's say there's 100 students total at this engineering school. Okay, and then so we'll say there are 70 men and there's 30 women. Okay, and just for simplicity's sake, I'm going to change these proportions to this, okay? And we'll just say you're one of these, at this school, you're only one of these three races, okay? And so, let's say so if out of the 100 students, 50% are Caucasian, that means we have a total of 50 Caucasian students, okay? And that could be, that 50, this could be broken out into 25 men, 25 women. It could be 35 men, 15 women. It could be a bunch of different, there could be a bunch of different ways to make up these, the 50% Caucasian. So let's say this is 35 men and 15 women, okay? And I don't know, let's say there's some special scholarship that this school offers, okay? That somehow, I don't know, a prominent person at the school graduated, and there's like, I want to set up a scholarship for Asian women or something like that, okay? And so let's say for the 20% Asian, okay, so that we have a total of 20 Asian students. Let's say, I don't know, 10 are men and 10 are women, okay? And that means we have a total of 70, so that means we have 25 men who are black and 5 women who are black. Okay. So in this case, we can ask, is being Caucasian independent from gender? Is being Asian independent from gender? Is being black independent from gender? Okay, and we can ask and find out. So knowing something about one event gives no additional information about the other event, or that would be our definition of independent. So if we look at, let's look first at the Asian category here, okay? And so we can ask, what is the probability of being Asian? Or actually, better yet, so we know what's the probability of being a woman if you're Asian, okay? Versus what's the probability of being just a woman in general, okay? So again, if we just randomly pick one of the 100 students at random, the probability of that randomly selected student being a woman is 30%, 0.3. Okay. All right. If we randomly select a student and then we say this student is Asian, okay, or if we just say we're going to randomly select one student from the Asian students, okay, so there's 20 Asian students, 10 are men and 10 are women, then that means the probability of being a woman or selecting a woman, given that that student is Asian, is 50%, okay? Does this make sense? Okay? And so here, the event that a student is Asian and their sex is are not independent, okay? At this school, knowing the fact that you're Asian means your chances of being, I guess, selecting a woman at random is a little bit higher than selecting a woman at random in general, okay? And then, we just made up the story that this school offers some sort of scholarship or something like that, okay? If we were to look at, however, the event of someone being Caucasian and being a man, this could be the probability. So we could say probability of selecting a man knowing that the student is Caucasian, and then probability of selecting just a man in general. So probability of selecting a man in general, out of 100 students, we have 70 men. So 70 out of 100 is 0.7. And then selecting a man knowing that he's Caucasian, there's 50 Caucasian people, and 35 of them are men. So we have 35 divided by 50, and that's going to be 0.7. So the probabilities here, or the proportions here, are exactly the same. So that means knowing, in this case, this particular race, knowing if a student is Caucasian or not, does not give us any more information about knowing what sex or gender this student is. Okay? Does that? So these are so in this case, Caucasian. The event of being Caucasian and the event of being a man are independent. Okay? And in this case, the event of being Asian and the event of being a woman, and also because the man thing is also affected, those are not independent. This is neither independent nor disjoint, okay? And then because you can only be classified in one of 3 races, these are all disjoint. Okay, yes?
So for the purpose of, say, the exam, it would be clear that if it's disjoint, it's mutually exclusive?
Yeah,
So
disjoint
something like
and are
race.
mutually exclusive are same thing. I'm
Right.
sorry?
So the questions that people tend to have with race is that it's tricky.
Yeah. So this was not a very good example just because,
So it would be clear that it
Yes,
would be mutually
yes.
exclusive.
Like picking an M&M color would be
disjoint.
Yeah.
Yeah, you can't, your M&Ms, okay, should not be more than one color, okay? Okay, so that's that, and then let me talk a little bit about tree diagrams, and then we will get into chapter 18. 19. Okay, is that okay on independence and disjoint and goodness? Okay, so sometimes some things are best illustrated with tree diagrams here, okay? So a tree diagram basically has a node, and then it produces a couple branches, okay? It could produce 2, 3, 5, however many branches, okay? Each of these branches are disjoint, okay? You're either going to go down one branch or you're going to go down the other branch, okay? So in I think in so I'm going to look at problem 43, okay? In chapter 15, okay? Chapter 15, number 43, okay? So here it says at a restaurant, there's three employees that wash dishes, okay? Okay, we have Al, Betty, and Chuck. Okay. Al washes 40% of the dishes. Betty washes 30%. And Chuck also washes 30%. Okay, so the first part of the question just says, we have 3 dishwashers. And we've got Al, Betty, and Chuck. Al washes 40%, Betty washes 30%, and Chuck washes 30%, okay? So if I just abbreviate all of these to A, B, or C, then we have the probability of A being 0.4, probability of B is 0.3, and then the probability of C is 0.3, okay? A, B, and C are all mutually exclusive. They're all disjoint, okay? If a dish is washed by Al, it cannot have also been at the same time washed by Betty, okay? Now, of course, we reuse dishes and things like that, but in this, we're simplifying our scenario and just saying that on any given day, if the dish was washed once, it was just washed by one person here, okay? Now, now people it's possible for someone to break the dish, okay? So the probability of breaking a dish, we actually don't know the overall probability of breaking a dish, but we know each person's dishwashing habits, okay? And Al breaks only 1% of the dishes, and it says Betty breaks only 1% of the dishes, and Chuck breaks 3% of the dishes, okay? So these are all conditional probabilities, okay? When it says Al only breaks 1% of the dishes, what we're saying is that the probability of breaking a dish, which I'm going to write BR, given that it was Al, so probability of breaking the dish knowing that it was washed by Al is only 1%, okay? And the probability of breaking a dish knowing that it was washed by Betty, so probability of breaking a dish given Betty is also only 1%. And the probability of breaking a dish knowing that it was washed by Chuck is 3%. So with this tree diagram, so if I just asked you what's the probability that a dish breaks in general, it's actually kind of difficult to know because we have the dishes broken by Al, the dishes broken by Betty, and the dishes broken by Chuck. And so there's different ways to, 3 people can break the dish. So to calculate the total probability of just having a broken dish is a little bit difficult. But the tree diagram we're hoping will help. So from Al, a dish can be broken or it can be not broken. So I'm going to have BR and not BR. Betty can break her dish or not break it. And same with Chuck. Broken or not broken. So 1% of Al's dishes are broken, okay? Which means the remaining portion, 99% of Al's dishes are not broken. So we put 99 here. Okay, is that all right? Same thing with Betty. 1% of her dishes are broken, 0.01, and not broken, 99%. And Chuck, 3% of his dishes are broken, which means 97% of his dishes are not broken. So now we have a total of six categories, okay? We can have dishes broken by Al, dishes that are not broken by Al, dishes that are broken by Betty, not broken by Betty, dishes that are broken by Chuck, and not broken by Chuck, okay? So if Al washes 40% of the dishes and 1% of his dishes are broken, that means the total amount of dishes that are broken by Al is 0.004. Okay, and the way I got that, that's equal to 0.40 times 0.01. Okay, so if Al washes 40%, 1% of those dishes are broken, which means 0.4 times 0.01, giving me 0.004 of the dishes are broken. Okay. Again, 40% of the dishes are washed by Al. 99% of those dishes are not broken. So we have 0.40 times 0.99, giving me 0.396. So in the grand total, about 4 in 1,000 dishes are broken by Al, and 0.396 are dishes that are washed but not broken by Al. Okay? And so following the same math here, I get 0.003, 0.297. That's 0.3 times 0.01 for the dishes broken by Betty, 0.3 times 0.99 for the dishes not broken by Betty. Okay, and then for the dishes broken by Chuck, I do 0.3 times 0.03, and I get 0.009, and which means I have 0.291 here, which is 0.3 times 0.97. Okay.
And all of that would add up to 1.0.
Yeah, if we add up all of these, all 6 of these categories, okay, and all 6 are mutually exclusive, or disjoint, they would all add up to 1.0. Okay, are there any questions on this? Yes?
Just in terms of writing, I don't know what you call it, the acronym, probability would be Al, that slash mark, given that he wouldn't break.
So it's the probability, you have to write probability of breaking given Al. Okay, this is what's given to us, okay?
Right, but the 0.04, how would you write that? What would be the name for that? Probability Al that it broke?
This?
Yeah.
This, oh, okay, so this is equal to the probability of a dish that is broken and was washed by Al, okay? So this is an and right here, and Al washed, okay? So this is an and. And this 0.4, that's the probability of Al. And this 0.01, that's the probability of broken given Al. So if we're just going to use the symbols, which might be better, we got probability of BR and A. Okay, and then I'm just going to write probability of A times the probability of BR given A. Okay. And all of these follow the same. Okay, and this would be the probability of not BR, or BR complement and A. And that's the probability of A times the probability of BR complement given A. And I don't have those listed out, but, well, maybe it's not completely obvious, so I'll just write, if the probability of breaking given Al is 0.01, the probability of not breaking, or BR complement given Al, is 0.99. Okay, and that's how we calculate all of these things. So let me just slide that up. Okay, so we have all 6 of those things. So again, so now if we just ask what's the probability that a dish is broken, okay, there's 3 ways a dish can be broken. It can be probability that a dish was broken and it was washed by Al, plus the probability that a dish was broken and it was washed by Betty, and a probability that the dish was broken and it was washed by Chuck. And we found all of these numbers. So the probability, so if there's 1,000 dishes, okay, Al breaks 4 of them, Betty breaks 3 of them, and Chuck breaks 9 of them, okay. That total probability is 0.004 plus 0.003 plus 0.009. Okay, and these are, so again, broken by Al, 0.004, broken and was washed by Betty, 0.003, and broken and washed by Chuck, 0.009. This adds up to be 0.016. Okay, so 1.6% of the dishes are broken. About 16 out of 1,000 are broken. 16 thousandths. Yes?
So is it true that because there is no overlap, that implies that they are disjointed?
Yes.
Is that more or less the definition? If they don't overlap, then they're disjointed?
Yeah, if there's no overlap, they're disjoint, okay? But, so broken by Betty and broken by Chuck, those are disjoint events. Those are these, each of these 6 over here are disjoint, okay? But being washed by Betty and being washed by Betty and breaking or not breaking, those are not disjoint, okay? And they're not independent either, because the probability of breaking depends on who's washing the dishes. Okay, so don't worry so much about the disjoint and independent stuff. At this moment, we're worried about calculating these probabilities. So if we ask, what's just the probability that a dish will break? 1.6% of the dishes break, okay? And that's because even though only 1% of Al's and 1% of Betty's dishes break, Chuck breaks 3%, and just the way, based on their proportions of washing, 1.6% of the dishes break, okay? So we can ask now, what is the probability that Chuck washed the dishes? Chuck was responsible for the broken dish, okay? So this is asking, what is probability that a dish was washed by Chuck if the dish is broken? Okay. Notice that this is different from this. This is the probability. What is the probability that a dish will break if it's washed by Chuck? Okay, so here we're saying we know that Chuck is washing the dish. What's the probability that it's going to break? 3%. Over here, now we're saying we know that the dish is broken. So what's the probability that Chuck was the one washing it? Okay, different questions here. Yes? Okay, so here, go on.
It's just 9/16, no?
Yes, 9/16, exactly. So here it's going to be, so Chuck, 0.009 of that proportion are dishes that are washed by Chuck and end up breaking, divided by the total amount of dishes that end up breaking. And so here this ends up being 9/16, which I'm not entirely sure what it comes out to be. 0.5167. I don't know. 0.5625. Okay. Okay. All right, so this is, and the way we got this was Chuck's 0.009 of all the dishes combined are dishes that are washed by Chuck and end up breaking, dividing by the total amount of dishes that were broken, okay? And we use the probability tree to help us find these numbers, okay? So the book's got a couple good examples in there, and I did one of these in your homework, so please make sure you understand that problem. Okay. All right. Okay. So let's we'll get started on chapter 18. Okay, so this is chapter 18. Okay, so in the book, it starts off with an example, and it says it polled U.S. adults, and they asked the question, do you believe in ghosts? Okay. So the poll asked, do you believe in ghosts? And so one institution called Harris, the Harris Poll Group, they asked 889 adults and 40% said yes. And then CBS News asked 808 adults and 48% said yes. Okay. So why the difference? Okay. And we're going to assume that both groups followed the proper random sampling procedures to make sure that the people that they selected were selected randomly. Okay. Okay. And this, so the answer is we're not going to worry about bias because, yeah, we're just going to, because that'll just mess up the idea here. So let's say both of these samples were unbiased. Okay, we just randomly picked them. So why does one group say 40% and the other poll says 48%? Yeah.
Perhaps the CBS poll is taken out inside of a scary movie with ghosts inside.
Okay, so that's going to get into bias, okay? So when you have a scary movie and you don't do the poll properly, okay, you're going to get bias, okay? But let's just say we followed the random selection procedures properly and we still got these results, yeah.
Don't they have like a plus minus
Mm-hmm.
on each?
Okay,
every
but
poll?
where does that plus minus even come
Well,
from?
They each had a plus minus of 4.
Okay.
Roll variability.
Yeah, okay. So the difference is just that the fact that the people selected were selected randomly, okay? The difference is people are selected randomly, okay? And just because things are selected randomly, different things can happen, okay? Just imagine, okay? Everybody, let's say you pull out a quarter, okay? And I tell you, flip the coin 20 times, okay? Flip the coin 20 times, so just say, okay? Some of you will get 10 heads and 10 tails, and so your proportion of heads will be 0.5, okay? You get 10 out of 20, you get 0.5. Okay? Some of you, just because when you flip a coin, it's random, you might only see 8 heads and 12 tails, okay? So other people, they might see 8 out of 20, and so their proportion of heads will be 0.40, okay? And so just by the random nature of the coin, everyone's going to observe a different proportion here, okay? And the same idea is here, except instead of flipping coins, we're asking people, and they're either going to say yes or no. Yes, I believe in ghosts. No, I don't. Okay? And so instead of looking at heads or tails, we're getting yes or no's. And just by the random nature of selecting people randomly, Harris might have selected, just randomly selected people that where fewer of them said yes, and CBS might have randomly selected a group where more of them said yes, okay? Just like some of you might happen to flip the coin and get a fewer number of heads, and others of you will get an equal number, and some will get even more, okay? So all of these are not hard to imagine, right? It might be hard to imagine somebody getting 20 heads out of 20 heads, or 20 heads out of 20 coin flips, but 10 or 8, not that unusual. And so just by the random nature of things, we might observe differences, okay? So if we, so let me turn on this computer here, and we'll try a simulation here. So we'll see how well this works.
Lectures from the previous week didn't go up?
Yeah, I had issues with the video. I'm trying to get them fixed, but the video didn't work out. Okay, so here, I don't know if I can make this any bigger. Is there a way to zoom? Control plus. Yeah, just it's only changing the font size there. Is it? It's not changing this size though. Yeah, I don't think so. That thing is staying the same size. You just let me see.
There's an application and accessories called
Magnifier.
on the top screen, or the top of the screen.
Let's see. Oh goodness. Oh, that's it? I can only do 200% or not? Okay, well, I guess that works, right? You guys can see? Okay, 200%. There's just a magnifying glass here. Okay, so what we're going to do is we're going to simulate, I don't know, whatever, tan Reese's Pieces here, okay? So when you buy a bag of Reese's Pieces, you can either have yellow, tan, or brown. Or I guess orange. Yellow, brown, or orange, okay? So what I'm going to do is I'm going to take, let's just say the true proportion that is orange is 40%, okay? So 40% of the M&Ms or Reese's Pieces are actually orange, okay? And then 60% are yellow or brown. We don't really care. Okay, we're only interested in the 40%, and I'm going to take 25, just randomly draw out 25 pieces here, okay? Sorry, I'm tongue-tied here. All right. So this is exciting. All right. Okay, so pulled out 25 Reese's Pieces, and then we count up. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them were orange. So if we do 9 divided by 25, the proportion that were orange is 0.36. Okay? All right, and so what we do is we actually plot 0.36 right here on our number scale here. So the true value, they put a little red arrow, is at 40%, but here we're plotting a little dot at 36%, okay? And then so I can do this again, and just by random chance, let's see how many orange. So in this case, 10 of them turned out to be orange, okay? And so I plot, we do 10 divided by 25, we get 40% are orange, and so I plot a little dot at 40%. Okay, so instead of spending all day clicking these one at a time, I'm going to just speed things up, and let's draw 100 out, or let's just draw 10, okay? So here I drew 10, okay, and then two samples had sample proportions of 36%. Two samples had sample proportions of 40%, okay? This one sample, this most recent one, had a whole bunch of orange, okay? And that was just because of random chance. And so we plot out 64% here, okay? And so let's just keep going here and just see what this looks like. So I'm taking lots and lots of samples. So after 600 samples, okay, so all the dots kind of merged into bars now. Okay, we can see a lot of the samples came out close to 40%, okay? A few had a few more, and a few had a little bit less, okay? And we're getting bars because you can either only have 10 orange pieces or 11 orange pieces or 12 orange pieces or 9 orange pieces, okay? So if you do 10 divided by 25, you get 0.4. If you do 11 divided by 25, you get 0.44. So it's not possible to get anything in between 0.4 and 0.44. Okay, so you can't have 41% orange M&Ms if you're only taking, or 41% orange Reese's Pieces if you're only taking 25 pieces to begin with. Okay, so that's why we have separate bars. But what does this overall shape kind of look like? It kind of looks like the normal distribution, right? Okay, and so this is the idea that we're going to start looking at here, and the idea is we've got something that's like a proportion 40%, or if it's 45% of the people believe in ghosts, or 80% of people, I don't know, households own a television or something. Okay, we can take random samples, and each of those samples, even though we're only going to observe one, those samples will have a sampling distribution. Okay, and that sampling distribution is what those proportions are. Yes, it is possible to have a sample where 64% of the pieces are orange, okay, but those are pretty rare. It's possible to get a sample where 12% of the pieces are orange, but those don't happen very often. Most of our samples have between 30 and 50% being orange, okay? Should I do this again, or does this do it again, or does it make sense? Or it's good? Or I didn't understand what people said there, but okay. So that's it. And we can try. So we can try different different sample sizes. So here, so notice the scale goes from 0.1 to 0.7, and we really only observe samples that go from 12%, 72%, and most are between 30 and 50%. Okay, let's say instead of drawing 25 M&Ms at a time, I draw 100 M&Ms at a time. Okay, so let me just do one. Okay, so this is 100. I keep saying M&Ms, but 100 Reese's Pieces. Okay, so in this case, we count up all of our Reese's Pieces. 41 of them are orange, and so our sample proportion is 0.41. Okay, and so we put a dot here. You can already see that the scale has changed already, kind of ruining the surprise, but whatever. Okay, so let's do 10. So we draw 10 here. And this sample turned out to be 42% orange, and we just keep going. Okay, so let's see. All right, so this is after 400 samples, okay? And again, it's not perfectly this normal distribution, but the overall shape is unimodal and symmetric, okay, with a peak in the middle, and it gets smaller outward, okay? And actually, if we fit the normal curve over it, okay, it actually fits the normal distribution quite well. So that's after 40 samples, and you can see that in this case, our range goes from 0.3 to 0.5, okay? It's not before when we only took 25 M&Ms or 25 Reese's Pieces, our range went from 10% to 70%, and we really only saw samples that went from 12% to 72%. Here now we're really only seeing samples that go from about, this looks like 27%, okay? And we only saw one of them all the way out to about 55%, okay? And that's because the overall proportion, the true proportion in our candy machine is 40% orange. So we expect that whenever we take a random sample out, that sample is going to reflect the true proportion of about 40%. But here we're observing just by the random nature of drawing samples, sometimes we get a little higher proportion, sometimes we get a smaller proportion. Okay, and we can just keep going and just seeing if, I don't know, let's see what this computer can do. This is what I do for fun. Okay, all right, and we can see this follows the normal distribution pretty well, okay? All right, so that was our, how do I get out of the magnifier now? It's not, escape doesn't work. Oh, I clicked the magnifying glass itself. Oh, look at that. Okay, good job. Okay, and then we'll put on presentation that's all black. Okay, how are we doing on time? So it turns out okay, so if you draw random samples of the same size, which we did, we first drew a bunch of random samples that were of size 25, and we drew like 600 of those, okay? And then later on we cleared out our experiment and we did the same thing again. We drew a bunch of random samples. This time, each of the samples were of size 100 with the Reese's Pieces, okay? So we're gonna call that number, whatever size our sample is, we're gonna call that N. It turns out that if you draw random samples of the same size, okay, and see the distribution of the sample proportions, okay, and we're going to call that P hat. So again, the sample proportions is we draw 25 Reese's Pieces, 10 of them are orange, so we do 10 divided by 25, 40% of our sample is orange, or we count 11 orange Reese's Pieces. So 11 divided by 25, 44% of our sample is orange. So if we look at the distribution of those sample proportions, okay, that distribution follows the normal model. That's what I want to say. It follows the normal model. Okay. And then let me, but I have to add certain assumptions apply. So it follows the normal model. Okay? So how do, so the normal model is the thing where it follows the normal distribution. And how do we define the normal model? There's two parameters that tell us what our normal model was. I'm sorry?
Unimodal and symmetric.
Okay, unimodal and symmetric, that talks about the shape. But how do we distinguish one normal model from another one? Because all normal models are unimodal and symmetric, yes?
The standard deviation and mean.
Yes, the mean and the standard deviation, okay? The normal model is defined by the mean and the standard deviation. Okay, so yes, all normal models are unimodal and symmetric, okay? But we've got a unimodal, we have a normal model for men's heights, we have a normal model for women's heights, okay? And what distinguishes one normal model from the other is the mean and the standard deviation, okay? And so, whenever we're looking at random samples of the same size n, and we look at the distribution of those sample proportions, okay, the mean of those sample proportions is equal to p. This is the population proportion. Okay. And the standard deviation is the square root of p times q divided by n, okay? And q is equal to 1 minus p. And again, p is the population proportion and n is the sample size. So again, let's talk about our Reese's Pieces. And I never know how to spell Reese. I don't know. R-E-E-S-E-S? Reese's Pieces? Okay. I was having so much trouble, like, huh? Okay, Reese's Pieces. This is Pieces. Okay. So let's say n is equal to 25, and so we said the true proportion is 40% of Reese's Pieces are orange. Okay, so 40% of the Reese's Pieces are orange. Okay, so what this is, together with this, it says if we took a whole bunch of samples, okay, the mean is going to be p, which is 0.4, and the standard deviation is going to be equal to the square root of p times q over n. So in this case, we have the square root of 0.40 times q, which is 1 minus p, so 0.6, divided by n. N is 25. So 0.2, it's almost going to be 0.1, but it's going to be like 0.098 or something. I don't even know. Q is 1 minus p. Okay, so 0.4 times 0.6 divided by 25. Actually, I have a calculator. We'll find out what it really is instead of me just making numbers up. 0.4 times 0.6 divided by 25. Wait, I messed something up. square root of that 0.0979. Yeah, so indeed, 0.098. Okay? So again, when we saw the distribution, we saw that it could only actually take on certain values. It could only take on 0.4, 0.44, and things like that. But the general idea is that if we took, if we look at the distribution, it would indeed follow the normal model here. Okay. And did you have a question?
If the mean were 0.6, it would have the same standard deviation?
Yes. If the mean, that's a good observation. If the mean, or p, was 0.6, the mean would still, the mean would be different, but the standard deviation would be the same. We would have 0.6 here and 0.4 here divided by 25. It would have the same standard deviation. So that's an interesting thing about these things. But yes.
Is there some limit to the standard deviation that's acceptable for a sampling?
I mean, there's no rule for what's acceptable or what's unacceptable. You just have to know that this is the standard deviation that you're going to get, okay? And if you're just trying to find a ballpark figure, then who knows? Maybe the standard deviation is acceptable. If you need something precise, the standard deviation might not be acceptable, okay? So it depends on your purpose. So all this means is that, again, we would place the center at p, 0.4, and then we can go out, what, one standard deviation in each direction. And so this takes us to 0.498, practically 0.5. Okay, and over here we have 0.302. And then we go, and so within here, we're expecting about 68%. That same idea. We go out 2 standard deviations, 3 standard deviations. The same things about the normal distribution apply. Okay? And again, this is the sampling distribution. Okay? Please be sure you understand what a sampling distribution is. Okay? The sampling distribution is we're taking random samples, okay? So any one sample, if I just take out 25 pieces, that single sample could have, just by random chance, it could have a proportion that's, 56% orange M&Ms. It could be out here, all right? Any single sample could be wherever. But if we looked at the overall distribution of what these samples are, some samples will have an unusually high amount of orange pieces. Some samples will have an unusually low amount of orange pieces, okay? If we look at the overall distribution of these samples, the sampling distribution, it would follow the normal model, okay? And again, we've got some certain assumptions apply, but so let me talk about that right now. But is the idea of a sampling distribution okay? All right. Okay. Well, and because now we have this normal model, I can say, if you know that the sampling distribution looks like this, what is the probability that when you take a random sample, that sample happens to have a proportion that is 60% orange, okay? 60% orange or higher. And you can find that just by, change it to a z-score, and you find the percentage that's higher, okay? And that would be the approximate proportion of samples that have that proportion or higher, okay? We'll have some example problems that get into it. Okay, so the assumptions. Assumptions and conditions. Okay, so that okay. So we have some assumptions and conditions so that the normal model fits, okay? I mean, you don't have to write this down, but I'm just going to give you a silly example. Let's say for our for the M&M, or not the M&Ms, but the Reese's Pieces, let's say my sample size was 2, okay? So I would only take out 2 Reese's Pieces at a time, and I said, what proportion is orange, okay? And in that case, if I only have 2 pieces, all right, I can have none of them being orange, and I would have 0% orange. One of them could be orange, and I would have 50% orange, or both of them could be orange. And then I would have 100% orange. And those would be the only 3 values I could possibly take on. And so my histogram would have a bar at 0%, 50%, and 100%. Okay, and that would not be, the normal model does not fit this, okay? So in some cases, the normal model will not work, okay? And so that's why we have these conditions. All right, and assumptions, okay. All right, assumption number 1. Independent samples. Okay, the sampled values are independent. And this assumption appears quite frequently in statistics because a lot of it depends on it. This is just like when we were talking about the adults who were polled about whether they believed in ghosts. We're already assuming that those adults that were sampled were independent. We're assuming that we didn't just ask a whole bunch of adults that came out of a scary movie all at the same time. That would ruin the independent samples assumption. Okay, we're just assuming that they were sampled independently. Okay. All right, sample size assumption. Okay. Okay, and right now we're just going to leave it at n is large enough. And we haven't really explained what large enough means, but with that silly example where n was size 2, that is not large enough. Okay. Okay. So n is large enough. The way we're going to figure this out, this is we've got the success failure condition. Okay. So here we're going to say this is n times p must be greater than or equal to 10, and n times q must be greater than or equal to 10. Okay. So this is one of the conditions for n is large enough, or n is the right size. Okay. So for example, with our Reese's Pieces example, n was 25 and p was 0.4. Okay. So if we do 25 times 0.4, n times p is equal to 10. So in that case, 10 satisfies the condition that n times p is greater than or equal to 10. Okay, it just barely makes it, but it satisfies the condition. Okay, and over here, we have n times q is greater than or equal to 10. So we also have to check that. So n is 25, q is 1 minus p, or 0.6. So if we do 25 times 0.6, n times q is equal to 15. So, and that's also bigger than 10. So in that case, both np and nq are greater than 10, so our sample size condition, or our success failure condition, meets. Okay. And then we have the randomization condition and the 10% condition. Okay, randomization condition, this is just for experiments, and just to make sure that the experiments are done properly, okay? Okay, when you create an experiment or design an experiment, you're assigning treatments randomly, okay? So the randomization condition just makes sure that you're treating the assignments properly, okay? And the 10% condition, this just means we're not oversampling, okay? This is to make sure we're not oversampling. Okay, so if there's 100 people in the room, okay, we want to make sure we're not drawing more than 10% of the population. So if our population is 100 people, so we're just curious, out of our 100 people, what proportion believes in ghosts or something. It would be easy to just ask all 100, okay? But if we want to look at a sampling distribution and things like that, we shouldn't ask more than 10 people at a time, okay? Just because when you start making your samples too large, it's going to alter things, okay? So to make sure we're not oversampling, okay, so make sure your sample size Okay, so make sure your sample size is less than 10% of the general population. That's your 10% condition. Okay, let me do one more example, and then we'll take a break, and then we'll come back for more exciting sampling proportions. Or not sampling proportions, sampling distributions. Okay, so the CDC, the Center for Disease Control, says that 20% of 18-year-old women in the United States have a body mass index of 25 or more, okay? And that's apparently associated with increased health risk, okay? So 22% of 18-year-old females greater than 25. Okay. This is the population, 22%, that's the population proportion P. Okay, so let's say at college, it asked 200 randomly selected female students to report their heights and weights, and so they could calculate the BMIs. Okay, so we had n is equal to 200. We asked at a college 200, and of the 200 students sampled, and of the 200, 31 had BMI greater than 25, greater than or equal to 25, I should say, greater than or equal. It's not as big of a deal, but 31 had BMIs greater than 25, okay? So is this proportion unusual? Okay. Is the fact that the college observed 31 out of 200 unusual? Okay, so first of all, if the college observed 31 out of 200 students, what is the sample proportion of this college? So the sample proportion, this is p hat, that's equal to 31 divided by 200, 0.155, okay? So 0.155 is lower than the national average of 22%, okay? So is that unusual, or is that within the realm of pretty likely or whatnot? Okay, that's what we're asking here, okay? So first, we just want to make sure that our conditions are met, okay? So here, the randomization condition, we said that 200 students were sampled, and if they were sampled randomly, then our randomization condition is met, okay? So let me just say check conditions, okay? So before we can really do any kind of analysis, we have to make sure that the normal model, we can use the normal model in the first place, okay? So the randomization, that works, okay? 10% condition. All right, so what does this mean? So in this case, as long as the college has more than 2,000 female students, then we haven't violated the 10% condition, okay? But if there's only like 500 female students, okay, then 200 is too large of a proportion. So as long as we've got a lot of female students, more than 2,000, our 10% condition is okay, okay? If college has more than 2,000 female students. Okay, and then the success failure condition or sample size assumption, okay? So n, in this case, n is 200 and p is 0.22. So 200 times 0.22 gives us 44. And then n times q is also going to be greater than or equal to 10. It's going to be 200 times 0.78, which is even bigger. 152. Or I don't know. Something. 172? I don't know. It's big, okay? So a big number. I think 156, but anyway, that's also bigger than 10. So we're okay. 156. Okay, so we observed 31 out of 200, or a sample proportion of 0.155, okay? And here we've got a normal model. So because all of these conditions are met, we can use the normal model, okay? And the normal model, where's the mean? The mean is going to be at the population proportion p of 0.22, okay? The mean is not at our sample proportion. The mean is at the population proportion, okay? And what is our standard deviation here? Square root of p times q over n. So the square root, p is what? 0.22. Q is 1 minus 0.22, so 0.78. And n is 200. N is our sample size. So we have 0.22 times 0.78 divided by 200. And then we take the square root. I'm getting 0.029. Okay. Yes?
Quick question about the 10% condition. So did you say that it was the sample size?
Yeah, we want to make sure our sample size is not more than 10% of the population.
Not more.
Okay? Or less than 10% of the population, okay? All right. So how do we determine if this is really unusual or not? We look at our normal model. Our normal model is centered at 0.22, and we have a standard deviation, sigma, equal to 0.029. Okay, we are out here at 0.155. This is our sample proportion. So what is our, how do we determine if this is unusual? Yeah, so let's find its z-score. So how many standard deviations away from the mean is this? So our z-score is what? Y minus mu divided by sigma. So the point of interest is 0.155. Our mean is 0.22. And our sigma is 0.029. And when we do this calculation, okay, we get z is equal to negative 2.24. Okay, so z 0.155 is about 2.24 standard deviations away from the mean. Okay. So in this case, this is pretty unusual. Okay. Because 95% are within 2 standard deviations, and here we're outside of 2 standard deviations. We're a little over 2 standard deviations away, okay? So this college is either unusual, or our sample is either just one of those very unusual samples. We just happen to draw an unusual sample, or maybe there's something about this college that is different from the general population, okay? Maybe the people here have a lower BMI than the rest, or whatnot. We have a question.
How did you get the 0.78 for Q?
Q is 1 minus P. So P is 0.22, and if you do 1 minus 0.22, you get 0.78.
What's the cutoff? Is it 2 standard deviations is the cutoff?
Unusual is a subjective term, but in general, we'll say about 2 standard deviations. If it's within 2 standard deviations, we'll say it's not so unusual. If it's beyond 2 standard deviations, it's a little bit unusual. And if it's beyond 3 standard deviations, it's really unusual. Okay. Okay, so why don't we, we'll take a break and we'll resume maybe around 8:45.